Okay, so today we're going to talk about distribution of the sample mean. So we have a sampling distribution, and that is a probability distribution for all possible values of a statistic that is computed from a sample size of n. So again, we're talking about statistic. We are not talking about a parameter. So sample versus population, sample size is n. The sampling distribution of the sample mean. This definition is really important because we're also going to do sampling distributions for other statistics, not just the mean. We just happen to be using the mean in this case, but we won't always be using the mean. So what a sampling distribution is for a statistic is the probability distribution of all possible values where our sample mean is actually our variable. So we talked about how we would change, the labels on our curves that we're drawing, and we've had X and we've had Z. So now what we're actually going to be doing is using X bar as our random variable. So this is going to be X bar computed from a sample of size N from a population with mean mu and standard deviation sigma. So when we have a simple random sample of size n that we take from our population with our given mean and standard deviation, here is what is true. The mean of all the X bars, so basically the mean of all the sample means, is equal to the population mean. So it's important, again, let me say that again, how we read this guy right here is the mean of all the sample means. And what we have found, when I say we, I mean lots of very smart mathematicians and statisticians, is that when you look at a sampling distribution for all the sample means, that ends up being approximately equal to the population mean overall. So that is a reason why we would find the mean of the sample means, because then we can have an approximation for the population as opposed to only for the samples. Now, the standard deviation of the sample means is not equal to the population standard deviation. There is a formula. It is equal to the population standard deviation divided by the square root of the sample size. This little symbol here is called the standard error of the mean. So this sigma sub x bar, or the standard deviation of the sample means, is called the standard error of the mean. Now, in order for us to be able to use these formulas, which again, the usefulness is that we can apply data from samples to inferring things about our population, but we're only allowed to do that when it is reasonable. And it is reasonable if the requirements here are met. First, the sample has to be a random sample. So generally they will say randomly selected or in a random sample of. So almost always requirement 1 is going to be met. Requirement 2, the sampled values have to be independent. So we've talked multiple times about independent. That was one of the qualifications we had in chapter 7 as well. So if we are sampling without replacement, then obviously, technically, those are not independent, but there's a second way we can fill the second requirement, and that is by checking that the size is less than, so the sample size is less than 5% of the population. So in formula terms, that means that if we're sampling without replacement, meaning that we can't just automatically say that they're independent, the way that we can meet this requirement is by verifying that little n, the sample size, is less than 5% of the population size. So it makes sense that if our random variable x is approximately normal, then of course the sampling distribution of all the sample means should also be normal. But the purpose really of everything we're doing in the last 3 chapters is what if our random variable is not normally distributed? So what is in here are some screenshots, and this one on the left is the original data set. Very clearly not normally distributed, very skewed to the right. We can see that. When we take n equals 4, so sample size of 4, and they repeatedly take samples of size 4 and then show the distribution of the sample means, look at how it's already less skewed. When I increase that sample size up, and I think that says n equals 10 maybe it says 20. But again, it's moving, and look how much less of a tail is on that right side. Now when we hit n equals 25, that distribution of the sample means looks very normally distributed. So this is why we want to verify requirements, because even though very clearly this original data is not normal, it is not normally distributed at all, the distribution of the sample means is normally distributed as long as our sample size is big enough. So that discovery led to what is called the central limit theorem, which says that regardless of the shape of the underlying population, so it could be very skewed, just like what I just showed you in this example, the sampling distribution of the sample mean becomes approximately normal as the sample size increases. So if the distribution of the population is unknown, so meaning we don't know what the shape is, or if we know it, but it's not normally distributed, then the distribution of the sample mean is going to be approximately normal. Regardless of how skewed the original data is, the distribution of the sample mean will for sure be approximately normal, provided that the sample size itself is greater than or equal to 30. So we will check that it meets the requirements, random sample, either independent or sample size less than 5% of the population. And then even if it's not normal, if our sample size is greater than or equal to 30, we can say it's going to be approximately normal because of the central limit theorem. I would very much put a star by this guy because, and I'm going to show you, the type of examples that you typically might see on the final or, concept checks, etc., because it's important not necessarily that you just know what the central limit theorem says. We should know that, but it's important that we know how to apply it. So example 1, determine the mean of the sample means and the standard deviation of the sample means from the given parameters of the population and sample size. So this is using the 2 formulas. So right up here. And the first one, super easy. If the population mean is 52, then that means that I automatically know that the mean of the sample means, make sure that we use the right notation, is going to be the same. It's also going to be 52. So no work to show there. We just know that those are equal. Then for the standard error of the mean, or sigma sub x bar here, the formula says that that should be sigma divided by the square root of n. So my sigma is 10 and my n is 21. So I'm doing 10 over the square root of 21. And of course, I will consult a calculator for that because I do not know that off the top of my head. And it says approximately, if I go to 3 decimal places here, 2.182. We typically on these will carry at least 3 decimals, mainly because we're going to have to be using this as an approximation in StatCrunch. So if we round too early, then our answers will be less accurate. So we're going to, if you want to write a note to yourself out here in the margin, round to 3 decimals, that would be the minimum we would want to carry. So answer the following questions for the sampling distribution of the sample mean shown at right. So again, notice this guy, put a little highlight on it. The label on the axis is now X bar. So this is the distribution of the sample mean, not of Z, not of just continuous random variable X. This is the distribution of X bar, or the sample mean. So the mean of all the means, I just have to look, well, what's the center? Oh, it's 15. So again, no work to show there. We've got that answer. Sigma sub X bar, again, that is standard deviation of the sample means. Because we've noticed that this is labeled sample mean, that just means, all right, how far is it from 15 to 15.6, or from 14.4 to 15? And the difference there, the distance, is 0.6. So that is what we will put here. So 0.6 would be our standard deviation of X bar. C, if the sample size is n equals 4, what is likely true about the population? So this is a very popular way to word this question, and until you've been prepped for it, it can be a little bit confusing, but that's why we're talking about it in the notes. So hopefully you won't get tripped up in the homework or on concept checks or, on the final exam. In order to know, because this is the distribution, it looks normal. We can only, again, going back to this, we can only assume that a distribution that was skewed to begin with will look normal if the population size is greater than or equal to 30, because at small sample sizes, 4, 10, it's still looking kind of skewed. Again, at 25, it's pretty close. It's greater than or equal to 30, that it should look normal. So if it already looks normal at n equals 4, what that is telling us is that it is likely, and again, notice that the word likely is in the description here, but what is likely true is that the population itself is likely normally distributed. Because if the original population was heavily skewed at n equals 4, this shape would not look like a bell curve. So part D, if the sample size is n equals 4, what is the standard deviation of the population from which the sample was drawn? So this is a working backward type problem using the same formula that we used in example 1. The difference is that here I know the sigma sub X bar, that's 0.6. And what I don't know is the population standard deviation. So sigma is what is staying my variable. I still know my sample size, but it's not the same as example 1. Here, sample size is 4, so square root of 4 should go in the denominator. So, of course, the square root of 4 is 2. So, really, all I'm doing is 2 times that 0.6, and that is going to be equal to my sigma. So 2 times 0.6 gives me 1.2 for that standard deviation. Okay, hopefully those guys make sense. We are now going to go to example 3, which kind of sees how we want to apply this. It says the reading speed of second grade students is approximately normal with a mean of 90 and a standard deviation of 10 words per minute. What is the probability that a randomly selected student will read more than 95 words per minute? This is actually the exact same type of question that we did in chapter 7. So if you draw the normal curve, it said normal, it gave us a mean, it gave us a standard deviation. So I've got 90 here, and then I am going up and down by 10 as I go, right? So I get to 100 and then 110 on the other side, 80, 70, etc. So this first problem reads no different than what we've been doing. So I would draw the curve. I would say, okay, 95's here, do my shading to the right. Can't do this very well using this tool for the screencast, so apologize for that. And then when I go to type out what my StatCrunch work would be, what I'm finding is the probability of my random variable x being greater than or equal to 95. And I know it's typed weird because it's faster to type than to use the writing tool. So this is what I'm doing in StatCrunch. That has not changed at all. I go to stat, I go to calculators, I go to normal, and I type in that information. So 90 for the mean, 10 for the standard deviation, change the symbol to greater than or equal to, make it the correct number, which is 95, press compute. There it spits out my answer. This is no different than what we've been doing. So 0.3085 is what I would record here for my answer. So 0.3085. Then B, what is the probability that a random sample of 12 second grade students results in a mean reading rate of more than 95 words per minute? So this right here is what is new for this chapter. Put lots of stars by this. You will see this. You have to be on the lookout for this on the final, on the concept checks, anywhere in the homework, because this is the probability that the mean reading rate is more than 95 words per minute. So it's not the same problem. What we did in chapter 7 and what is in part A is just for a single randomly selected student. I need the probability that the mean from a sample size of 12 is more than 95 words per minute. So what do we do differently? What we do differently is instead of this being random variable x like it was in A, I now have random variable x bar. So you are going to have to draw these curves, right? We've talked about that over and over. Important that you draw the curves. The mean is still going to be the same. That's because the mean of the sample means is the same as the population mean. So that's not changing. But I have to calculate sigma sub x bar using our new formula, and that is what I have to type in to StatCrunch. So sigma sub x bar is going to be the sample or the population standard deviation, which was given as 10, divided by the square root of the sample size. And in this case, it said sample of 12. So square root of 12. So 10 over the square root of 12. Again, I need to carry 3 decimal places. Otherwise, your answers will be slightly different, which again, we generally want to have the consistency there. So 2.887 would be this guy. And so when I go to StatCrunch, what I am then doing is typing in a totally different standard deviation. So I go back. The mean is obviously still 90, but I'm adjusting this standard deviation to now 2.887. I'm still doing the same probability. It's just representing something different. And look how much smaller the probability is, 0.0416. Now, intuitively, so 0.0416 is what we said. This should make sense intuitively. And you would label the curve, by the way. It's very hard for me to do that on the video. I apologize. But we've talked about how important that is. This is so much smaller because it is much more likely to have a single randomly selected person have a certain value than it is for the actual mean of the sample to have that particular value. Much more difficult the higher number of, people or things that we have to get in agreement. So C is the exact same idea, except we're just changing the sample size. So again, the higher the sample size, the lower the probability should be. So I'm writing out my sigma sub x bar again, this time 10 divided by the square root of 24. And so this time what I'm typing into StatCrunch, everything's the same except for that standard deviation. Now it's gone to 2.041. That's what I got when I did 10 divided by the square root of 24. So now I'm going to type this in instead, 2.041 compute, and look even smaller still, 0.0071. So if we type that out, 0.0071 is our answer. And there is, again, you can see it drops as we go. So what effect does increasing the sample size have on the probability? So we just showed that by increasing the sample size, we made the probability lower because, again, we're making it more difficult to have that mean have a certain value. So increasing the sample size decreases the probability. Because, why is that happening? It's because the standard deviation is smaller. And so the smaller the standard deviation, the more compact those 3 standard deviations from the mean would be. Part E, a teacher instituted a new reading program at school. After 10 weeks in the program, it was found that the mean reading speed of a random sample of 20 second grade students was 92.8 words per minute. What might you conclude based on this result? So again, what might you conclude? There are lots of things that you might conclude. But what we want to look at in this case would be the probability of having that level of words per minute. So if we want a random sample of 20 second grade students and finding out what the probability of that would be, we can type those values in. But what we do see is that the mean reading speed was more than the population standard deviation. 20 is a pretty high sample size. And so we can conclude that possibly we are going to have, more success than the average, if you will. So we might conclude that the reading program increases speed more than the average, which is what we would say there. There is a 5% chance that the mean reading speed of a random sample of 20 second grade students will exceed what value? So this is a working backward type problem, and we did a lot of these in chapter 7. So we're doing probability, and we have to write X, even though we're using X bar, because that's what is happening with StatCrunch, is that we're always using X. But we're looking for the value. We have the percent, so we are going to type this into StatCrunch. Now, before we can do that, we have to make sure that we've calculated the correct standard deviation. So again, population standard deviation is 10, and the square root of the sample size, which is 20 here. So the standard deviation that I'm going to type in is 2.236. So I'm going to StatCrunch. 2.236 is the value that I'm going to be using. So 2.236. And I do not know what this value is now, but I do know the percent is 0.05. So then I press compute, and it spits out for me 93.677, so about 93.7 words per minute. So 93.7 words per minute. All right. And I think that is where I'm going to have to cut this off, because I am approaching the deadline of the 30-minute recording. So if we have additional questions, I will record example 4 separately.